Students, I welcome you in today's session of physics. As you can see here, we are going to discuss chapter number 9, which is your work power and energy. Clear? So, first we talk about what we have to study in this chapter. This is your syllabus. So, you can see here work done by a constant force and variable force. The first one. After that, you have to study about the kinetic work energy theorem, power, potential energy of a spring, conservative forces, conservation of mechanical energy, that is kinetic and potential energy. After that, we have to cover out conservative and non-conservative forces, concept of collision, elastic and elastic collision in 1 and 2 dimensions. So these are the things we have to cover out in this chapter. So first we talk about here. You can see what is work. Clear? So this is work. So whenever a force acting on a body produces a change in the position, clear, of the body, so we can say that work is said to be done by the force. Clear? If there is no change in the position of the body, work is not done. We may exert a large, there is an example given here. Suppose that if you exert a large force over a wall, but if the wall remain intact at its present position, then what happened? Work, you can say that work, we have not done any work because there is nothing displacement over the wall. So if a coolie, same example is given here, if a coolie having a heavy box on his head is standing at a fixed place, he is not doing any work. Fine. So the scientific definition of work done by a force is somewhat different. What is the definition? You can see here, this is the definition. Work is said to be done only when a body acted upon by a force move actually through some distance in the direction of the force. So this is the definition of force. Clear? And you know very well in the previous classes, you know the concept. What is work? Work is equals to force multiplied by displacement. So if the displacement is there, then you can say that work is done. And if the displacement is not there, then you can say that work is not happened. Fine. Now we come to the, you can see here, this is the topic 2, work done by a constant force. So work is measured by the product of the applied force and the displacement of the body in the direction of the force. Clear? So you can write it, that is the thing I have already told you. Work is equals to the force multiplied by displacement in the direction of the force. Clear? So that this is the thing. So if a force F acting on a body produces a displacement in the body in the direction of the force, you can see here from the figure number A. Here there is an object, this one, and we applying the force over from this in this direction. And what happened? You can see it displaces by a smallest distance, and the new position comes out to be this. Fine. So that is the thing written here. If you apply a force on a body and it produces a displacement by the application of the force, the body in the direction of force, then the work done is equals to how much? Work done is equals to force multiplied by displacement. Now come to the second one, which is your B figure. You can see from this figure, if the force is making an angle theta with the direction of the displacement of the body, means in which direction displacement is going on, and you are also applying the force in through an inclination of theta, then you can see this is the horizontal component of F cos theta with of the force. I hope you know very well the resolution of vectors. So from there, this is comes out F cos theta, and the vertical component, this one, is your F sin theta. So you can write this equation. First you can see there work is equals to force, and the force we are taking at the horizontal component, which is your F cos theta, and S is your displacement. So finally what relation we get here? Fs cos theta. So this is your equation number 1. Clear? Now because F cos theta is the component of F in the direction of the displacement, you can see here the displacement is also going on in the direction of the force. So force and displacement are both have vector quantities. I hope you know very well what are vector and scalar quantities. So by the definition of scalar product, the scalar product of force and displacement, you can write it like this: force and displacement is equals to Fs cos theta. Clear? Now here you can see that theta is the angle between force and displacement. Fine. So what we get here? Work done is equals to force multiplied by displacement. So work is the scalar product of force and displacement and is a scalar quantity. So you know very well the scalar product of two vectors is the, what we get here is scalar quantity, because if you dot product take the vectors of f and s, then finally you will get fs cos theta. Now we will talk about the dimension. I am just telling you in the brief. This is the dimension ml square t minus 2, clear, and it's absolute unit. The SI unit of work is, I hope you know very well, is joule, clear. So you can see here 1 joule, there is a relation between joule and Newton is equals to 1 meter. So 1 joule equals to 1 Newton multiplied by meter. If we talk about the CGS system, so what happened in the CGS system? The work the unit of work is comes out to be erg, this one. And what is the relation between erg and dyne? So this is the relation of 1 erg equals to 1 dyne multiplied by 1 centimeter. This is the important one. You should remember this relation between joule and erg. So this is the relation 1 joule is equals to the 10 to the power 7 erg. Clear? Now we talk about what is gravitational unit. So gravitational unit of work in SI is kg meter and in CGS is gram centimeter. So work is said to be 1 kg meter if a force of 1 kgf displaces a body through a distance of 1 meter in the direction of the force. That is, you can say here 1 kg meter is equals to 9.8 joule. Clear? Similarly, the work is said to be 1 gram or centimeter if a force of 1 gf displaces the body through how much distance? 1 centimeter in the direction of the force. So that you can write it like 1 gram centimeter is equals to 980 erg. There is also a relation given here, relation between kg meter and gram centimeter. So you can write it 1 kg meter is equals to 10 to the power 5 gram centimeter. Fine. Now you can see this nature of work done in various situations. The fourth point we are going to discuss. So work done is given by, you know it very well, work is equals to fs cos theta. Therefore work done is positive, negative or 0 according to the angle, that is theta. So if theta is an acute angle, means less than 90, obtuse greater than 90 or 90. So the work done is 0 when either f or s is 0. You can see from this formula, if anyone either force or displacement is 0, in that case your work done will be comes out to be 0. Now we talk about the example of the positive work done. So when a body fall freely under gravity, that is theta is equals to how much? 0. So work done by the gravity, you take it positive. Similarly, the second one, when a lawn roller is pulled by applying a force along the handle at an acute angle, in that case the work done is also positive. Fine. Now you can see here what is the example of negative work done. So when a body is thrown upward, its motion is opposed by gravity. The angle theta between the force and displacement is how much? 180 degree, which is your obtuse angle. Therefore the work done by the gravity is taken as negative. Clear? Now see the second one. The example number second, you can see here, when a body is made to slide over a rough horizontal surface, the motion is opposed by which? Friction. So hence the work done by the friction force is considered out to be negative. Clear? Now you can see, we will talk about here example of zero work done. When you call the work done is 0. So here you can see that the few points given here from this. When a weightlifter holds a heavy weight on his shoulder for a few seconds, or a man presses a rigid wall with a force, the work done is either case is 0, since there is displacement caused by the applied force is 0. Same thing, this thing we already cover out, the example of Cooley. We are moving to the third one. When a satellite revolves in a circular orbit around the earth, then in that case theta equals to how much? 90 degree. So the work done by the gravitational centripetal force on the satellite is 0. Fine. Now come to the fourth one. An electron moving in an empty space free of electromagnetic field does no work as there is no force on it, that is F is equals to 0. I hope you understand it. Now here you can see there are the few figures given here. This is the work done in case of variable force. When you apply the variable force, then what happened in that case? This is not so much important one, so I am skipping this. And we are going to discuss about the conservative and non-conservative. So first one, you can see here what is conservative and non-conservative forces. In this case, first we talk about the conservative forces. So a force is said to be conservative if the work done by the force or against the force in moving a body depend only upon its initial and final position of the body. Clear? And is dependent of the path followed by between the initial and final position. So in that case we considered it that is a conservative force, or you can say that this as a path independent. For example, here you can see that there are multiple examples given here. The gravitational force is a conservative force. To prove this, let us calculate the work done against the gravitational force in raising a body of mass small m through a height small h from its initial position A to the final position B. Clear? This you can see that this is the initial position of the body at point A and at the final position at point B. And the height between A and B is equals to how much? Small h. So from the figure you can see the 3A, it is written here, this is the figure 3 and this one your A. The body is being raised vertically upward, hence the work done against the gravitational force is how much? Mg. Clear? So you can write it this formula by using the work done is equals to force into displacement. So force is equals to how much? Mg, and the displacement in the body is through upward direction is how much? G. Now come to the figure 3b. You can see here we are talking about this one figure. The body is taken along a smooth inclined plane. Clear? Inclined plane, which is your CB. You can see here this is the inclined plane CB. And AB of the height of A to B is how much? Is small h. And inclination with the base is theta, or the horizontal is theta. The force required against the gravity is equals to mg sin theta. So how much force you have to require to raise this body in through the inclined plane? You can see here from the figure this one mg sin theta, because you are moving the body from C to B, and the mg sin theta, the component of the force, is in the opposite direction. So you have to equal this force so that you can easily move the body at point B. Fine. So from the hence you can write it, the work done is equals to how much? Work done is equals to force into displacement CB, and CB is equals to, you know it very well, mg sin theta, and in place of B you can write it using the relation of trigonometry h sin theta. So finally you will get here mgh. Now see the figure number C. This is the body is being taken through the same height. Again we are taking the body through the same height, which is your h, small h. Clear? Over a staircase. Now we divide into the multiple staircases. So let there be n staircase of vertical height h dash around the horizontal width, and width there is one staircase is of width small x, you can see from this figure, and the height of one staircase is we considering here h dash. So the work done against the gravity in raising the body vertical up to the each staircase is how much? Mg h dash. Clear? And that in taking through each horizontal distances small x is 0. So the total work done in raising the body through the h staircase is W is equals to mg h dash and multiply by the number of staircase, which is your small n. So finally you will get here mgh, because h is equals to n times of h dash. Fine. Now you see the figure number D. This is the figure D. What happening in here? A body is being taken along a zigzag path. Fine. The body is moving along a zigzag path through the small height AB, which is equals to h. So this path may be assumed as made up of large number of small horizontal paths, each of delta x. Clear? And vertical paths of how much? Each delta h. Since the work done against gravity along any horizontal path comes out to be 0. Why it is 0? Because there is nothing motion going out to be in the horizontal direction. Clear? The total work done along vertical paths will be added up. So you add up all the vertical distances, which is your summation of mgh, and the final expression comes out to be mgh. Thus the work done in moving a body against the gravity depends only on the initial and its final position of the body, and not upon the path followed. So hence gravitational force is a conservative force. Other example of conservative force are elastic force, electrostatic force, and magnetic forces. Clear? So you can say that an important property of the conservative force is that that the work done by a conservative force in moving a body through a complete round trip is zero. Why it is zero? Because you know very well, if we move around a circle, then the displacement comes out to be the zero. That's why here the conservative force in moving a body through a complete round trip is assuming to be zero. Clear? Now you can see here, suppose a particle acted upon by a conservative force, this from this figure number 4, goes from position A to the position B along the path A1 to B. Clear? And return back to position A against the force along the path B to A. Since the force is conservative, so work done does not depend on the path. You know it very well, as I told you while teaching that conservative forces is independent of the path. The work done against the force taken negative along the path B to A, that is, you can write it like this. Clear? Now you can see here, force is a conservative force. So a force acting upon a particle is a central force if it is always directed toward away or from a fixed point, and its magnitude depend only on the distance of the particle from that point. So gravitational force between two masses, electrostatic force between two charges, and magnetic force between the two magnetic poles are example of central forces. I hope it is clear. So students, this is all for the today's class. We will discuss the remaining non-conservative forces. You can see here our next topic in our upcoming lecture, that is lecture number 2. Till that, do study. Thank you class. Thank you very much.